In Chapter 13, we talked about vector-valued functions. Remember, a vector-valued function is one where we put in an input, usually t, or we could put in whatever we want here, and we spit out a vector. But we could view this not as spitting out a vector, but actually just spitting out multiple outputs. Maybe an xy or xyz, depending on what dimension we're talking about, or even we could go with higher dimensions if we wanted to. We'd probably just then do x1, x2, x3, and so on and so forth. But we can definitely easily view this as just taking in a single number and spitting out multiple numbers. In this chapter, we're going to kind of turn this around. We're going to look at functions where we plug in multiple numbers and we spit out one number. We call such a function of several variables, or frequently also we call these multivariable functions. And this could look something like f of x1, x2 to some xn, depending on how many variables we're plugging into the function. And the result of this will just be a single number that we'll get out. Now, of course, in this class, we're not going to go too far with this. Just like with our vector-valued ones, we limit ourselves to xy or xyz. Here, we'll usually look at functions of two variables. Something like f of xy, or three variables. F of xyz. And it'll turn out that functions to two variables are fairly easy to work with. Functions of three variables are still kind of important, but they're going to be a little bit trickier to work with. That mainly has to do with how things will be graphed later on, and we'll describe how that works. But before we even get into graphing these, we need to talk about the domain of them. So the domain of these functions are not going to be just intervals. They're not going to be just sets in the real line. We actually need to work with points in the plane or three-dimensional space, depending on whether we're doing two or three variables. So I'm going to draw here an example for two variables, but it will kind of extend to three variables as well. So we can view the domain of a function of two variables as some set in the plane. We could say our domain is this blob here. This will contain all the points x, y, that make sense to plug into our function. If the formula would break for points outside this region, then they wouldn't be in the domain. Sometimes we might actually even restrict the domain and say that we only care about points that are in a particular set, but that's us kind of restricting our domain to a particular thing. If we don't give a domain naturally, we'll have to look at the formula and figure out what would be a good choice there, or we have to figure out what points actually make sense to be able to be plugged into our function. If we're working in three variables, we, instead of having this flat thing, we'd have like a blob in three-dimensional space. And I'm drawing them as blobs, but they don't actually have to look like that. They could be very different, which let's look at some examples of such things and see what are the possibilities. So let's look first at a relatively easy function. F of xy is going to be, let's say, x plus y squared. This function, we can take two numbers, x and y, plug them into this formula, and we get a number out. And in this particular case, since we just have a square and a sum, there's not really any restrictions on what x and y can be. No matter what x and y I pick, I can plug them in there and I get a result. So you can actually say the domain of this one is in fact the entire plane. Now we wouldn't say that's all real numbers. You might say that for a one variable function that works for every x that we plug into it. Here, we're going to use the notation r squared, or r2. This is a notation that we generally use for the entire plane. So r represents all real numbers is just, say, one axis. Here, because we have two axes, we have an x and y, we have r2. You can also say r3 when we have three axes. So if you're working with a function of three variables whose domain is everything, doesn't have any restrictions on what you can plug in, you could say its domain is r3, or r cubed if you want to read it that way. Usually we read it as r2 and r3. Next example, here we're going to let f of xy be x divided by x squared minus y. Now, of course, here we have an issue if the bottom is ever equal to 0. If y is ever equal to x squared, then the bottom is 0 and we have a big problem. So we're going to have to exclude those points. But those are the only ones we have to exclude. So let's write this using our set builder notation. So we'll say the domain is all the points x, y. We can say they're in R2, though we could leave that part out if we kind of assume that we're working in R2. But it's going to be all the points x, y that satisfy the condition that y is not equal to x squared. That's our restriction on this function. We cannot plug any of those kind of points in. And if we were to draw the domain of this thing, we'd go ahead and draw the parabola y equals x squared. Though we're going to put it as a dashed line, kind of saying that even though we have to draw it here, this is not included in our domain. And our domain D is everything except for this dashed line. Now, if you look in the book on a lot of these examples, they actually put colors to denote what parts are in the domain, what parts aren't. That's a little difficult for me to do here, so I'm just going to kind of describe it. But the point here is that everything except for this dashed line is in our domain. Next example, again, we're just working with functions of two variables right now. We are going to take the square root of x squared minus y squared. This is another function of two variables, but there are some restrictions on what you can plug in here. If y squared ever turns out to be bigger than x squared, then we're going to end up with a negative number under the square root, and we don't want to have that happen. So you could say here, just to kind of describe what we're doing, we're saying all points x and y. We're going to leave out the in R2 part, just that's kind of assumed here. All points x, y, where x squared is at least as big as y squared. Though you could also say that this is a little bit more complicated than we'd like it to be. Another way we could actually write this that would actually make it a little easier to realize what this condition means is that the absolute value of x has to be at least the absolute value of y. If we ignore any negatives, then x is bigger than y is what we're essentially saying. If we go ahead and plot this, well, we think about what would that mean for x to equal y, or x to equal negative y? Well, we just have lines. And we can actually say, well, since we have greater than or equal to, we actually do include those lines. So instead of putting the dashed lines like we had there, I'm going to go ahead and put the solid lines. So here, this is the line y equals x. This is the line y equals negative x. If the absolute value of x is bigger than the absolute value of y, then we have to be further along x than we are along y. So we're actually going to include the part over here, and we can also include the part over here. But we don't want to include the parts up here or down here, because there we're further along y than we are along the x, ignoring whether we're going positive or negative. So here our domain is this quarter of the plane, this quarter of the plane, but not these two quarters of the plane. So kind of an interesting domain on that one. Last example we're going to do, at least for just domains anyways, going to look at f of x y is equal to ln of 1 minus x squared minus 2y squared. Now, similar to the last two, we have something that causes an issue. These are really the three issues that we can run into when we have division, when we might have a 0 on the bottom, when we have square roots, or any even root anyways, where we might have a negative in the root, and natural logarithm causes an issue if we put in a negative or 0 inside there. So here, we're looking at any point where the inside is a positive number. As long as it can put a positive number in there, we're fine. And so really we're just saying the domain is all the points x, y, where 1 is bigger than x squared plus 2y squared. Or we're going to go ahead and write that as x squared plus 2y squared is less than 1. And we have to figure out what exactly does that actually mean. If we were to plot this region, what would that look like? And really, plotting that region is easier if you think about what would this be if we actually had an equal sign there. X squared plus 2y squared equals 1. That's the equation of an ellipse. Specifically, this is the ellipse that it looks like. So the 2 in front of the y squared causes the y part to become a little shorter than the x part. If it was just x squared plus y squared equals 1, we'd have the unit circle. So we'll go ahead and plot that ellipse. Now, again, it is not less than or equal to, so we have to exclude the ellipse itself. Any point on that ellipse will not work in this function. So, like we did on 2, we're going to put a dashed line instead of the solid lines that we put on 3. And on 3, we could allow those lines to be in our domain. Here, we just have a dashed oval, and since it has to be less than, it turns out to be the inside of the ellipse. This is our domain. That one takes a little bit more thought and to figure out exactly what's going on with those. But it turns out that it's not too bad of an example. Now let's think about how we might graph a function of two variables. In fact, let's see how we could graph each of these 4 functions and figure out exactly what they look like, rather than just seeing what region of the plane works for their domain. Let's figure out what do they actually mean. And it turns out what we can do is that we can think of the output of our function. If we have f of x, y, we can think of the output as being z, and we can graph the point x, y, z. And that's just going to be points in 3 dimensions. So every single one of these functions is going to turn into a surface in 3-dimensional space. So let's actually go ahead and do that. So here we have our axes. We first want to graph our f of x equals x plus y squared. And GeoGebra just allows us to go ahead and type that in. If you type in x plus y squared, okay, I guess this version of it wants me to tell it more explicitly that we're talking about a function of two variables. Or maybe I could just have typed in z equals. Okay, apparently I'm getting more used to this new version of GeoGebra that I'm using here. Apparently, if you don't tell it when you first open the program that you want to do 3D graphics, it causes issues. I can't bring up the axes later and expect it to work. I don't know. I'm honestly having a few issues with GeoGebra lately, and I'm kind of not happy about it. So you might see me actually go back to the original version of GeoGebra that I was using before. But going back to the actual mathematics, what was it? We had z is equal to x plus y squared. And we end up with a surface. At every point x, y, if I put in a point, say 1, 2, that's a point in the plane. So you can actually tell it's down there in the xy plane. But then the z value that we get, if we plug in 1, 2 into x plus y squared, we get 1 plus 4, so 5. So the height of the actual surface above that point is 5. So if we plot the point 1, 2, 5, that's the point above the point 1, 2 that is on the surface. And that's what we mean by graphing these functions. Now let's look at the next one. So remember that one was the function x divided by x squared minus y. So here you can kind of see why our domain doesn't include the parabola, because there things are either going to one of the infinities, because we're getting zeros on the bottom. Now sometimes when infinities are involved with 3D graphics, GeoGebra does kind of give us this weird view of it. It's trying to somehow come to terms with things that are close to each other, that are very low negative numbers and really high positive numbers, and it can't really tell necessarily whether it should what it should do with those points. But at the very least, we get an idea of what this thing looks like. It's actually a really weird looking curve, or surface, I should say. But at the very least, we get an idea of what's going on. Let's move on to the next one. Next one was square root of x squared minus y squared. And again, along the edges, it's trying to come into terms with some of the points not working, some of them actually being there, and so it doesn't really show the edges very well. In fact, along the lines y equals x and y equals negative x, this does come down to 0. So it actually does have a very nice edge to it if we were to plot it correctly. GeoGebra kind of has some issues with some plots. And if we zoom out, it doesn't really change shape that much. But we can get a good idea of why the domain is what it is. Let's put in our third function. This time we have the natural logarithm of 1 minus x squared minus 2y squared. This one actually graphs a little nicer than the other ones, even though it has the natural log in it. And what you can kind of tell here is that the domain is definitely the ellipse. Let me position our axes like we normally have them. The positive x is the red one, the red arrow here. You can't really see the arrow on the y, but it's pointing up this way. We get our nice ellipse as our domain. But because the numbers that we're putting in here are 1 and lower, the biggest that we can actually plug in here is 1, then, and natural logarithm gives negative numbers when we put in numbers between 0 and 1, then the graph of the surface is all down below the xy plane. But it actually is a pretty nice looking graph despite working with natural logarithms. Now, along the edge of the ellipse, it is actually going down to negative infinity. We're only seeing part of this surface. It does continue down to negative infinity as we approach the actual ellipse. Now, we are actually very lucky that nowadays we are able to use computers to get such nice depictions of these surfaces. Back in the old days, they didn't have that capability. And what would they have done? Well, one thing that they actually do is they use what are called level curves. Basically, if we don't know how to graph the whole z equals f of x, y, we might be able to graph f of x equals some fixed k. Basically, this is going to be an equation that just involves x and y, and so its graph should be a curve in the xy plane. Just to kind of ignore the z for the moment and just set it equal to a k. You could actually view this as the cross-section of this surface with the plane z equals k. And that's exactly what that curve is going to be. So if we plot these kind of curves for various values of k, we can get an idea of what the entire surface looks like by essentially just looking at a bunch of its cross sections. This is actually a pretty common technique when you're drawing maps of various regions of the world, where you want to show mountains and valleys and stuff like that, and you basically draw the curves where different altitudes are. And in those situations, and even here, frequently those are called contour curves or contour lines. So let's go ahead and pick an example and see how this will work. So a nice easy example would be something like f of x, y is equal to x squared plus y squared. We want to know what this thing looks like. We'll go ahead and put in set this equal to various values. We could say let x squared plus y squared equal, say, negative 1. Or we could look at x squared plus y squared equals 0. Or x squared plus y squared equals 1. We'll put in a couple bigger values too. And so on and so forth. Now, of course, we didn't actually have to pick integers, but usually those are the ones you want to start with unless there's some issue with that. But let's just look at integers for now and ask ourselves, what do these curves look like? Well, this very first one, it doesn't look like anything. X squared plus y squared can never be a negative number. No matter what we put in for x and y, we'll never get a negative one out. So you can say this is empty. There's no curve there. Level curves don't have to exist for every k. Technically, the definition that the book uses, they specify that the k's here will need to be in the range of the function, meaning that there is going to be some output that gives that number. But there's no reason why we can't, if we don't know the range of our function, why we can't just set it equal to that number and then later on show that, no, this doesn't result in a curve. X squared plus y squared equals 0. This is also kind of interesting. It actually includes exactly 1 point. The only way we get 0 from x squared plus y squared is if both x and y are equal to 0 themselves. So we call this a level curve, but it is just a single point. Level curves can actually include just points. And those will usually correspond, well, those will correspond to, you could say, tops of hills and bottoms of valleys and stuff like that. In most situations, we won't know if that's going to happen. We'll get into how we could actually determine when that might happen later in the chapter. That will involve some actual calculus with these things. Now, of course, from that point on, we do recognize what these equations give. X squared plus y squared is the unit circle. X squared plus y squared equals, or did I say? I think I just said x squared plus y squared is the unit circle. X squared plus y squared equals 1 is the unit circle. X squared plus y squared equals 2 is also a circle with a radius of square root of 2. Then we have square root of 3, and so on and so forth. These are all circles. Specifically circles around the origin. And so, at the very least, what we already have an idea that everything here is nicely symmetric around the origin. This shouldn't be too surprising, because we did pick a fairly nice function here. But at the very least, we do have kind of an idea of what's going on. But let's actually plot these level curves. And what you could actually go ahead and just type in a bunch of these curves and see what GeoGebra spits out. But GeoGebra does have a fairly nice command here, sequence. Sequence allows you to do various things. It actually allows you to plot sequences like you had in Calc 2, but we're not going to be doing that here. I'm going to be specifically looking at these last two versions of sequence, where I can type in an expression, an expression meaning our function x squared plus y squared. I'm going to tell it, but I need to set that x squared plus y squared equals a variable. I'm going to use the variable k. I have to tell it what variable I'm going to be changing, and then I'm going to give it a start point for that variable and an end point for that variable. And if I don't want to be using integers, I might have to give an increment that tells it to do more often, pick more values of k between the start point and the end point. So showing this in action here, we have our x squared plus y squared equaling k. Tell it the variable of k. And I could start at -1. GeoGebra just won't plot anything for -1, of course, because there's no curve there. And let's even go further than 3. Let's go to, I don't know, let's go to 20. And actually, I don't really have to do anything more than that. It just kind of is already there. So what we can see here is that it's plotting all the circles from, well, from equaling -1 to all the way to equaling 20. So here, the point in the middle, that's the graph of x squared plus y squared equals 0. Then we have x squared plus y squared equals 1. That's our unit circle. X squared plus y squared equals 2. That's our circle of radius square root of 2. And so on and so forth going outwards. Now, I kind of wish that GeoGebra would allow us to denote which one of these corresponds to what heights, but at least in this particular case, we have an idea already that this is at height 0, this line is at height 1, then height 2, height 3, and so on and so forth. But you can kind of get an idea already of what's happening if you keep that in mind. And you can note here that as we go further and further out, the lines are bunching up. What that actually means is that our surface is actually getting steeper as we go further out. If we look at another example, so here I'm going to do another sequence with a slightly different function. I'm going to take the square root of x squared plus y squared, and we'll still equal k. So our function here, instead of being x squared plus y squared, is the square root of x squared plus y squared. Again, our variables k, and this time I'm actually going to go with, well, actually, I guess we still don't want to go to negative numbers because we can't get negatives out of that. So let's just start at 0 and still go to 20. And there we go. So this is a very similar expression, just with a square root there. And this time it's still circles, but the circles aren't bunching up. They're actually pretty evenly spaced. And so that's going to mean that this surface, even though it still has the same shape to its level curves, is actually going to look very, very different. So here, this is at a height of 1, this one's at a height of 2, this one's at a height of 3, and they're further apart as we go. Now, if we do want to plot these and see what that actually means overall, we can go ahead and use what GeoGebra allows us to do with three-dimensional plots. So here we have our three-dimensional axes. We're going to type in z equals x squared plus y squared. That was our first surface. Alright, so this is what we get from z equals x squared plus y squared. This is what we call a parabola. We actually talked about this back in chapter 12, at least a little bit. It has a cross-section of a parabola, but it just is rotationally symmetric around the origin. You might remember that we called things like this elliptical paraboloids, but that's when we have more, when our cross sections are actually ellipses and not just circles. If we just have circles, we usually just use the term paraboloid. If we look instead at the curve, or the surface with the function square root of x squared plus y squared, we instead get a cone. We actually get the, you could view it as just half of the cone. If remember, we were viewing z squared equals x squared plus y squared as being the double cone, where we have the cone going up and we have a cone going down. But since we wrote it with the square root on this side, we just get the top half of the cone. But what you can kind of tell if you compare the two, so down here around the origin, they're both increasing not too quickly, but the cone never increases faster. It just keeps going up at a very steady rate. The paraboloid does increase faster and faster as you go up. And so our level curves are going to bunch up the further away from the origin that we get. So we kind of have an idea of what's going to happen based off of our level curves. Let's look at another function. Let's look at f of x, y, is equal to sine of x times cosine of y. We're going to go ahead and make level curves again to see what this looks like. But this time we won't just use integer values of k, because remember, sine and cosine never give us anything outside the range -1 to 1. If we multiply them together, that doesn't change. The output of this function is always from -1 to 1. So if I were just plot along for integer values, we would get something that would be a little bit interesting, but it won't be as interesting as the whole thing. So I'm going to actually change my interval from being a 1 to 0.1. So we'll go ahead and here we change back to the two-dimensional stuff. Again, we're doing a sequence. We had sine of x times cosine of y, and it's going to equal a k. K is our variable. We're going to go from -1 to 1, but we're going to use an interval of 0.1. That will allow us to graph multiple curves where we're setting it equal to -1, -0.9, -0.8, all the way through 0.9 and 1. And there we go. So here we get this really fancy looking thing where you can see a lot of stuff is going on. Maybe we'll zoom in a little bit. Hopefully this doesn't lag too much. Yeah, when it plots a whole bunch of curves like this, it can get a little bit laggy. So the one issue with using GeoGebra for this is that it's not telling us which of these curves corresponds to which height. So if I look at this curve right here, is that representing the height of 2? Is that, or not a height? Maybe it could be 0.2. Maybe it could be 0. I don't know unless I know something about my function, and GeoGebra isn't really telling us. So what we're going to do, I'm going to go ahead and make a slider. Yeah, we'll call it A, I guess. It's going to go between. Actually, we're going to go from 0 to 20 with an increment of 1. Because what we can do here is we can use the. So what this is actually doing when we do a sequence is it's making a list of a bunch of different curves, but it's giving them one name. So L1 is the name of this list, and I can tell it to pick a particular entry on that list. If I go ahead and put in the slider A, it's going to give me the 8th position in that list. And let's actually go ahead and change the color of this. If it'll stop lagging as much as it is. I'm going to make this red. No, I didn't want to make another slider. Wait. No, color the axes red. I didn't want the axes to be red. Okay, here we go. So I have it giving me the particular curve for one height. So here, L1, that's the name of the list of 2. That's giving me the curve that has the formula sine of x cosine of x equals negative 0.9. Maybe I'll make that a little easier to see. Come on, stop lagging. Okay, so what we can basically see is that the sine x cosine y equals negative 0.9 is all the curves that are in red, because that's what I've done. Is I've essentially taken those and colored them red, or at least attached a red color to it. I think it's actually combining the red and the green somehow. As I move my slider, it changes which one of my curves is colored in red, because it's going along that list. It's starting at negative 0.9 and it's going through bigger and bigger values. So you can see the squares that have the red in them already, those are the ones that are going down into below the xy plane. As I increase, I eventually hit 0. So when the 11th one in the list apparently is where sine of x cosine of y equals 0, and that's actually the square grid that we have there. And as we go further, it starts going through the other squares. So now these other squares are above the xy plane. So we kind of get an idea of how this particular surface, sine x cosine y equals z, has parts. It essentially divides the entirety of the three-dimensional space up into squares with hills in some squares and valleys in the other ones, in kind of a checkerboard pattern. Let's actually plot this surface and actually see it in its entirety. Alright, so we type in z equals sine of x times cosine of y. and we get a surface that looks like this. So you can kind of tell that there is a grid pattern here where we have alternating hills and valleys, and just kind of an interesting surface that comes from our trig functions. Alright, I was going to do another one, but this video has been going on a while, so let's go ahead and move on. I don't want to start a new video for this next topic. So we already saw that we can plot these surfaces just fine using GeoGebra, and I did mention that back in the past they didn't have that functionality, and so that's why they looked at level curves. So why do we continue to talk about them now? Well, if we want to plot a function of 3 variables, so if we have f of x, y, z, to plot such a thing, we would have to introduce a new variable. Usually we like to pick w for the 4th variable if we don't do x1, x2, x3, and x4. But what we have here is it is something that we could plot technically, but we have to use 4 variables. And plotting such a thing would then require us to be in 4-dimensional space. Obviously, that's going to be a little difficult for us, so we can't really do that. So what we're going to do instead is plot essentially the level curves, though in this case they're actually going to be surfaces because we are dealing with x, y's, and z's in some equation equaling k. So we get level surfaces. And even if we can't visualize what's happening in 4-dimensional space, we can get an idea of what's happening by looking at what are essentially the cross sections of what that plot would be. Now, this time I'm not going to show, I'm going to go ahead and plot something, but I'm not going to show all the level surfaces at once. Not only are you already seeing that GeoGebra can be kind of laggy when trying to do a list of a bunch of curves, it gets even worse when it's trying to do a bunch of surfaces. But also because some of the surfaces will be behind some of the other ones, so it won't really be useful to show them all at once. But let's go ahead and work with a particular function, and we'll show some of the level surfaces. So let's just do x squared plus y squared plus z squared. Kind of the next step up from what we had. First thing I'm going to do is I'm going to go ahead and make a slider. I want a variable a. Let me position that a little bit nicer. I'm going to click over here. It'll make a slider. Let's actually make that a little bit wider for range. But here I can go ahead and pick a value. I guess I called it a. This will be the k that we are using. But we're going to go ahead and plot the surface with equation x squared plus y squared plus z squared. That's our function of x, y, z. And we're going to set it equal to a. Now, nothing showed up, but that's because the number that I'm plugging in there was -1. There is no solution to x squared plus y squared plus z squared equals -1. If I move that to positive numbers, it actually does go ahead and show us something. And as you might expect, x squared plus y squared plus z squared equals a number is a sphere. It's actually a sphere of radius square root of a in this case. And this actually grows pretty quickly at first, but slows down as we put in bigger and bigger values, and that actually represents the fact that the function increases more rapidly as you get away from the origin. This is very similar to our paraboloid from before, where it got steeper and steeper as you got out. Here we kind of have a paraboloid in 4-dimensional space. This we can't really visualize that. But all the cross sections, at least we know, are spheres. It's fairly nice. What if we look at a slightly different one? So here, this was our first example. If I put in, say, f of x, y, z is equal to, let's say, x squared plus y squared, but now minus z squared. Let's see what that one looks like. Or at least we'll see what the cross sections look like, these level surfaces. So x squared plus y squared minus z squared is equal to a. And we can see that what we get is a hyperbolic paraboloid. Or, no, sorry. Getting them mixed up. This is a hyperboloid of one sheet right now. And if we vary our a, it actually turns into a hyperboloid of two sheets. And right as it switches, it technically is a cone, but that's a little difficult to get exactly at 0. But technically, the cone is part of that. But all the cross sections of this four-dimensional surface are these hyperboloids and the cone, and it shifts between them as we go. So we might not have a good idea of exactly what this surface looks like, but we can get information about it using these level surfaces. Now, one thing I will warn you about here is that GeoGebra can't handle this for every function of 3 variables. If I were to go ahead and try the function f of x, y, z is 1 over x squared plus y squared plus z squared, it's not going to know how to handle that. GeoGebra doesn't really like what we call implicit surfaces so well. Basically, where we have some equation in x, y, and z equals a number, it prefers it to be in the form of z equals some equation in x and y for graphing a surface. It does recognize certain ones. That's why it can handle spheres. It can handle most quadratics, and so these first two were easy enough. For this last one, we might have to solve for z, or at least solve for some form that GeoGebra recognizes. In this particular case, I might start with setting this equal to a k, and then maybe flip everything upside down. We have x squared plus y squared plus z squared equals 1 over k. That is an equation for the same set of level surfaces, but this is now a quadratic. We can actually plot those. And so if we do that, this time we're doing x squared plus y squared plus z squared, and I guess not k, but we're doing 1 over a. Then as we look at various values of a, we can see that for a that is close to 0, we get really big spheres. In fact, at 0, it's going off to infinity. As we get to negative, there's no solutions. But as we put in bigger values of a, we get smaller and smaller spheres. It actually shrinks down to 0. So what we're basically saying here is that the function 1 over x squared plus y squared plus z squared is really close to 0 as we get further out. That's where we get small values of a, giving us a level surface. But as we put in bigger and bigger values, or as we put in points that are closer and closer to 0, we get bigger and bigger values. That actual function blows up near the origin. So basically, this is a way of getting an idea of what our four-dimensional graphs look like, even if our minds can't picture them, even if we can't depict them on a computer screen or anything like that. We can actually get some information about them that might be useful in various applications, because functions of 3 variables happen to pop up very frequently in various applications. One kind of example would be like you could talk about what is the temperature at a given point in a room. Well, if we're on the ground, it might be different than if we're up in the air. So knowing the temperature does depend on three variables, or x, y, and z for three-dimensional space. And we get an output based off of that. And that's an example where technically the graph would be a four-dimensional plot, but it's representing something that we can definitely have an idea of in three dimensions. So we do want to be able to work with those. But that's all we're going to be talking about in this section. We're not quite getting into calculus quite yet. Next section we'll talk about limits so that we can get into doing some calculus, but we won't actually be seeing anything about derivatives until 14.3. So leave that there. Sorry for the somewhat long video, but I didn't find a good stopping point in there. But hopefully it was interesting enough, especially with seeing me have to deal with some of these issues in GeoGebra. Still getting I guess we're kind of pushing GeoGebra to its limit. It doesn't really like to deal with three-dimensional stuff quite as much as it likes to deal with the two-dimensional stuff. And when we're plotting a lot of different things at once, it kind of tests its limits a little bit. But it does still give us a lot of good information, and a lot of information that would be hard to get otherwise. So we're going to keep using it. So see you in the next video.